Hey, welcome back. I've got another example here on using Supermesh analysis to find all of the branch currents in this circuit. So we've got three power sources, we've got three different loops, but the important thing here is we have a a current source in between two loops. And when you see this, and if you were asked to use mesh analysis, this immediately means you have to use Supermesh. So we can get started by labeling on a few things here. So we know that we're going to have a mesh current in each of the loops. And I also find it helpful to label on our branch currents. You can just assume the directions for them if you don't actually know them. In this case, we don't know them until we solve them. Except for the one on the right here, we do know it's going to be going this way because of this independent current source in this, it's all in the same branch. And then we have one more right here. So we can give these names. Let's just call them A, B, C, and D. And actually, let's kind of put them all on the side here so we can keep track of everything that we've got. So we know right away by inspection that I3 is going to be -2 amps. That's because as it comes around and it passes through this current source, it's basically just vector addition. It's going the opposite way and it has nothing else to do. So we just switch the magnitude and direction. So basically I3, the way that we've drawn it, is equal to -2 amps. The way that we drew IC is opposite to I3, and so we're actually going to log this one here as a +2 amps because we know we actually have we've assumed the direction correctly. And something else that is helpful to label on here is our polarities as well, based on the way that we assumed the currents to be flowing. So it's going to be like that, and this will be used later in the KVL. Now, in a regular mesh analysis problem that doesn't have a current source between two branches, the next step would be to find I1 and I2 by doing KVL around each loop. But because there's a current source in between them, and we can't use Ohm's law to determine what the voltage is across this element, then we need to basically redraw the circuit without this element, and that's going to make this whole loop a big supermesh. And we're going to just apply KVL the whole way around the supermesh, and we're going to use the currents that's flowing through each of these as they were on the original diagram. Now we should actually fill out what these currents are, basically from IA, and relate the branch currents to the mesh currents, or the green ones to the blue ones. I find it helpful. So IA is going to equal I1 because IA and I1 are just going through the same direction, just like that. Same thing here is going on with IB and I2. So this is equal to I2. I wrote this one in the wrong one. This is supposed to be for IC. IC is equal to 2 amps. My bad. And ID is just equal to the net, right? We have I2 going down and I3 going up and ID going down. So ID is equal to I2 minus I3. And then I1 and I2 are still our unknowns, and that's what we're looking for right now. We do have a relationship to connect them though, even before we go to KVL here, because we know that 1.5 amps is coming down, and we also have, again, I1 going down and I2 going up. So 1.5 amps is the difference of those in the direction of I1. So we just have I1 minus I2 is equal to 1.5. We can also rearrange that and just say I1 is equal to 1.5 plus I2. And this is going to be one of the equations that we use to find one of these unknowns. And the other equation that we'll use is KVL around the supermesh. So if we just start here, we're going to go into the negative terminal of the battery. So we're going to start with a -3 volts. And then when we enter in the next terminal here, it's going to be the positive terminal of the resistor. And the voltage across this is going to be the current times the resistance. Just a reminder, because V equals IR based on Ohm's law. So we have +2 times IA, and IA is just equal to I1, so we can jump straight to that if we want. And then when we come into the next terminal, we're entering the positive terminal, so we're going to put it as a positive down here. So we have +4 times IB, which is also equal to just simply I2. And then now when we come around the corner and into this one, we're going into the positive terminal again. So this is going to be plus the resistance, which is 2 ohms, times ID. You can write it if you want, but ID is also equal to I2 minus I3, so you can just substitute that right now. Times I2 minus I3, and that's all equal to 0, because once we come out the bottom, we're back into this same node, which is electrically common to the point where we started. So let's give ourselves a little bit more space to work here. And basically we can just simplify this problem quite a lot. It's just a lot of steps, and we'll see that 2I1 plus 6I2 is equal to -1. I think we can actually fit all of this in the screen, and let's just write this up here. So we have 2I1 plus 6I2 I2 is equal to negative 1. Well, now what we can do is we can substitute I1 here. So we have 2 times 1.5 plus I2 plus 6I2 is equal to negative 1. And we can further simplify this just to see that I2 is equal to negative 0.5. And then what we can do is we can take this I2 and we can directly plug it back into this expression. So we just have I1 is equal to 1.5 plus negative 0.5 amps. And I1 is just equal to, so if you were asked just to find the mesh currents, then we have them. I1 is equal to 1 amp, and I2 is equal to negative 0.5 amps, and I3 is equal to negative 2 amps. But if you were also asked to find the branch currents through the resistors, it's really easy because we have these relationships here already. So IA is equal to I1, which is just equal to 1 amp, and because we have a positive value, that means that we did get the direction correct and it is going to the right. IB is equal to I2, so IB is just equal to negative 0.5 amps, or what you can say is it's equal to positive 0.5 amps in the other direction, so going like that. I see we already determined that the current was 2 amps going to the left, and then ID is just equal to I2 minus I3. And if you're plugging those in directly, we have negative 0.5 minus 2, and that is positive 1.5 amps, or basically in the positive means we have the correct direction, which we assumed it to be going down, so it is in fact going down. So there you go, guys. That is another example on using Supermesh analysis. I personally prefer nodal analysis. I think it's really easy to get these negative signs backwards and make mistakes along the way. But anyways, I hope the video was helpful in case you're asked to solve a problem using Supermesh analysis.